Welcome to the webcast ChoConnect, Transparent and Efficient Chocolate Production. My name is Tobias Voigt and I'm working at the Technical University of Munich. I have the honor to introduce the ChoConnect project to you and also to guide you through the presentations of our partners. The ChoConnect Showcase was implemented to illustrate the advantages of a standardized network connection. For this, we used a standardized communication protocol based on Weihenstephan standards and OPC UA. We illustrated the advantages of the standardized connection at a demo plant. Originally, the showcase was planned to be shown at the Interpack fair, and therefore we decided to use a simulated demo plant. Let me just have a look at this plant quickly. What you can see here is the 3D visualization of this simulated chocolate production plant. It is a material flow simulation and it was set up on the Siemens software plant simulation. The plant for the demo application consists out of a temper from the company Sollich, a molding plant from Winkler and Dönnebier Süßwarenmaschinen, and also a buffering system and 2 packaging machines from Theegarten PACTEC. It was set up as a material flow simulation model, but is controlled via real controllers, in this case Siemens controllers, but it could be controllers from different companies also, and those controllers control the simulated line and they are connected each to each other via OPC UA servers and clients, and also connected to a superior manufacturing execution system. By this implementation we focused on the following use cases. We wanted to show that a standardized networking allows a decentralized line control. So thanks to this standardized networking, the individual machines in the line can react intelligently to the states of the others, also to the speeds of the others within the line, and this was realized via OPC UA servers and clients on the controllers of every machine. The second focus was the MES connection, where we want to demonstrate that the standardized interface provides all the necessary data for line visualization, measurement data display, also order control, and this by floating order change, and of course efficiency and OEE analysis. This also was done via the OPC UA interface, where the controllers of the machine act as OPC UA servers and the MES solution is a OPC UA client. This standardized interface of course should provide advantages to the users of chocolate production lines and all kinds of food production lines. We are believing that digitalization boosts the efficiency in confectionery production, and of course in the first step boosts the efficiency of the implementation of IT solutions and the line implementation. So a standardized interface should simplify the line integration vertically through to the MES line management system, and horizontally I showed the use case of the decentralized line control. This of course to increase the line yield and the line efficiency continuously. And what we also could see and learn in our demo project, the ChoConnect Showcase, is that simulation is a good tool to have a flexible line out planning and also to have a virtual commissioning of a line, what we used in this showcase. In the next presentations, our partners will present all those mentioned advantages and the steps of our showcase development in detail. Firstly, Christoph Nophut, also from the Technical University of Munich, will begin and introduce the Weihenstephan standards based on OPC UA to you.
My name is Christoph Nophut, and I'd like to tell you something about the Weihenstephan standards and our way to a companion specification for OPC UA. This work is supported by the VDMA. First of all, I'd like to introduce the Weihenstephan standards to you. The Weihenstephan standards cover three aspects in the classical automation pyramid. The first aspect is the definition of MES functionalities, so such like calculating KPIs, efficiency analysis, but also includes batch and article tracing and quality assurance. The second aspect the Weihenstephan standards covers are the description and the definition of data points which are needed for calculating such MES functionalities. And the third aspect is the communication between the machines and the MES. At the moment, we have an WS protocol. It's a proprietary protocol for the transfer of the data from the machines to the MES system. At the moment, we are developing and writing a companion specification for OPC UA to have an alternative communication protocol for our Weihenstephan standards. The Weihenstephan standards covers 4 different domains. The first is WS PAC, which was released back in 2005. WS Food was released in 2010. WS Bake in 2015, and the last in our domain is WS Brew, which was released in 2019. The data tag definition could look like this or in this way. This is an example of the WS PAC specification. We have a tag name. This name is unique, and we have a more common way for the operator. The name could also be in different languages. We have categories, so there's counter category. We have a closer look to the other categories in a few slides. Every tag has a unique tag number. This is from the past when with our WS protocol. So in common, every tag was defined over the tag number in the past. The data points could be read or write accessible, and we have a description of each data point. So in this example, the data point gives the number of the total packages which have been processed by the machine. In the WS protocol, it's just an unsigned number, and in OPC UA it will be an WS analog unit type. We have a closer look to this as well in the next slides. The Weihenstephan standards covers 4 domains at the moment, and in each domain we have a tree describing a lot of different machine classes and categories, and defining for each machine class which data point have to be delivered mandatory or which data points are optional for this machine. So in other words, we have a permutation table behind those trees, and that's an different compared to other companion specification on the OPC Foundation hosted, because if we would like to describe every single machine class, so we would have to write around about 150 different companion specifications. So we decided a little or a slight different way to describe our machines in the Weihenstephan standards, and it looks like in this way. So we have a layered model. At the end of the day, we'd like to have instances for different machine classes. For example, a filling machine from the WSPEC domain and cutter from the WS Food domain, for example. At the bottom of every server instance is the basement of the OPC UA foundation, the OPC UA meta models and built-in information models. On top of this, we are using the companion specification for devices and the companion specification for machinery. That companion specification we'd like to use for describing meta information about the machine and organizing our WS machines within the OPC UA server tree. We're using the PACML companion specification for having the state machine from PACML. So on top of this lies our companion specification. Our companion specification only define data types and the way how to structure our machines. The gap between the companion specification and our server instances we closing by so-called WS templates. Within template we have the data point definitions and the permutation table I showed you a slide before. So we have for each domain one of such templates, and so we may be flexible to add more domains or covering more domains in the future in the same way. The starting point for every Weihenstephan standard machine is the WS machine type. Such machine describes which WS version is used. So this version includes the domain and the version number. At top of this, every vendor could define data point for his machine by its own. So it's possible to add an WS vendor version or a WS project version for a special product or project. The WS machine class describes which class was selected out of our domain tree. The second information of the machine type is the identification. That identification comes out of the companion specification for the machinery, which was released, or the release candidate was published in May 2020. The last information the machine type organizes are the data points within different categories. I showed you before, each data point belongs to one category, and each category has an own functional group folder, so you can compare it like a folder on your file system, and each data point are organized within such a folder. The identification block in our WS machine type is from the companion specification for machinery, and it contains a lot of additional meta information about the current machine, like information about the manufacturer or the model, as well as information about the serial number. I'd like to introduce you the document structure of the Weihenstephan standards and a tool, the WS modeler, to organize and document all of our information within the Weihenstephan standards family. So starting point was the definition of MES functionalities. Such functionalities are defined in the document data evaluation and reporting. Each domain has its own document for such definitions, and we have the WS modeler, which we are working on. So the modeler contains all the information and definition of the data points within all our domains. It will replace at the moment, part 2 of the Weihenstephan standards. The modeler also containing the WS templates, which are replacing the libraries, and the templates describing the permutation table, which data points belongs to which machine class. And how this name is that already, the WS modeler is also a modeling tool, so you can create your own information model for a machine and creating configuration files for your servers. The companion specification for OPC UA for the Weihenstephan standards describing gives you an introduction to the OPC UA, to the Weihenstephan standards, and also information about mapping the WS protocol to the OPC UA protocol for the Weihenstephan standards, and defining the complex data type. One of those types is the WS machine type from the last slide. Within this companion specification and the modeler, you can create a notezet file. A notezet file is a XML document and describes the information model of a machine. We also have a document for the WS protocol. The WS protocol is the current way to communicate for the Weihenstephan standards, and it's also possible in the future to use such protocol. The modeler is capable as well to create a config file, the BDA config file for the WS protocol. We've also have a document, the WS acceptance test. What we are writing on is an implementation guide, so it describes the workflow from your idea to a running server with the information model of the Weihenstephan standards.
Let's have a closer look to the WS modeler. As I mentioned before, the WS modeler is an Excel-based tool. You see different data sheets. Here, one is the definition of all of our WS data points. At the moment, there are over 400 different data points defined for all of our 4 domains. And you see the templates with the permutation table. Let's have a look at one of those data points. For example, the WS current mode data point. We see the display name. This display names is in the current language of the operator to display information on the HMIs. We have the category of this data point and the tag number from the WS protocol. Here you can see the definition of this data point, and in this example there's an enumeration behind this data point, and you can get additional information at this button. So you can see that there are different machine states like off or manual, semi-automatic or automatic are defined with this data point. We have the information about the data types in OPC UA and the data type in the WS protocol. Let's have a look at our permutation table. So we see at the top our different machine classes and our data points, and we can see which of those data points are mandatory or optional for one of those classes. We'd like to have a new model, clicking at this button and get a new window. So we can select our domain and select one of our machine class, can give them a name and create a new model. So we get a new tab with some basic information. We can see our selected domain, our selected machine class. We can give them a name. We have information about the current Weihenstephan standard version and have an information block with the information from the companion spec for machinery. We have two sections with the configuration of the WS protocol or the configuration of WS OPC UA configuration. And we have a long list with all possible data points for this machine class. All mandatory data points are already selected, and we can add some more specific data points as we'd like for our machine. It is possible to add detailed information about the engineering unit, for example, for the temperature, so you can select it in degree or in Fahrenheit. As well, you see the basic information with the description and the tag numbers. If you're already done with your configuration, you can export your model for the OPC UA or for the WS protocol communication. In addition, you can export your model to an PDF, so you have everything documented for your customers. For the first implementation of our companion specification for the Weihenstephan standards, we choose an simulated plant for producing chocolate bars. So this is the production line in plant simulation. Beneath every single machine are an simulated or virtual PLC with this program running on, and we can connect via your expert in this case to one of the packing machine in this demonstration. We can browse to the folder machines. This is the way the companion specification for machinery defines the entry point for every machine. We have the packing machine, and I've choose some of the data points which the machine is provided, so we can see that the current state is operating and the current programs are in production. We see the speed of the machine. There's actually, there's a warning in the machine that's also simulated in plant simulation. We have the counter for good and bad, good and total packages, and we see that the current article ID is a dark bar, and the next production in the queue will be a milk bar. So you can see that the developed information model for the Weihenstephan standards are implemented in this demo.
So we can say with the companion specification for OPC UA for the Weihenstephan standards, we have an alternative for the existing WS protocol with the self-description of the machines. We are going one step closer to an IoT and Industrial 4.0 world, which everything and every server describing itself to the world. We finished the adaptation of the companion specification for machinery, and we are going to start the release process of our companion specification in December of this year. As you saw, we are working on a modeling tool, the Thaddäus modeler, to create easily information models for every Weihenstephan standards machine class. And we have done a first implementation of our information model with the ChoConnect Showcase. So if you have further questions about the Weihenstephan standards, don't hesitate to contact me.
Thanks to Christoph Nophut for this deep insights into the WS OPC UA companion specification. Now Thaddäus Rapp, also a colleague of mine, will follow. He will explain to you how this Weihenstephan standard OPC UA companion specification may be implemented into a machine controller.
Hello, my name is Thaddäus Rapp. I'm from the Technical University of Munich, Chair of Brewing and Beverage Technologies. In the next few minutes, I would like to show you our implementation workflow for OPC UA servers and clients for the ChoConnect project. In the first step, you will be needing an OPC UA node set. This can be generated, for example, by the WS modeler from our chair. Once you have acquired the fitting node set for your device, you need to map the variables in the OPC UA information model to your PLC variables. After mapping the OPC UA variables to your PLC variables and uploading the project to a controller with OPC UA server functionality, you are able to browse the server with any OPC UA client. For the ChoConnect project, we are using TIA Portal and PLC Sim Advanced because we are collaborating with Siemens. To show the third-party compatibility, we're connecting UA Expert to the OPC UA servers for browsing the data points later on. For our first step, the mapping of the variables, we need the OPC UA node set, Siome, short for Siemens OPC UA modeling editor, and the TI project with the PLCs. When we start up Siome, we can drag and drop our node set file onto the left-hand side labeled information module. There we browse to our device, in this case a tempering machine. When you select the TI portal mapping layout of Siome, you might see that some data points are already mapped. I will show you the mapping process with the remaining data points. First, we need to open the TIA project, select the PLC of the tempering machine and navigate to the data block containing the PLC variables. The different namespaces of the information model are locked to protect it against accidental alterations. By clicking on the lock symbol, we can unlock the namespace and modify it. For this demonstration, we need the namespace 1, ChoConnect, and namespace 5, Weihenstephan. The first data point I want to show you is called Next Order ID Outlet. It has the data type string. I simply drag and drop the WS Next Order ID out from the right-hand side onto the corresponding information model variable. The green light indicates that the type checking shows no data type conflict and the variable is correctly mapped. More complex data types are mapped the same way. Temperature zones, for example, is an array consisting of 8 real values. As long as the WS temp zones array is of the same size, it can also simply be dragged and dropped to the left. If we want to map the WS current mode variable to the current operating mode, we might get a data type conflict depending on the software version we are using. This is due to the fact that the information model expects the WS operating mode enumeration type. Should this occur, we do not only need to map the data point but also the data type. As you can see on the right hand side, there is a WS mode enum array. This array needs to be mapped to the WS operating mode enumeration type data type of the information model. Since Siome is still a work in progress, we actually can't simply drag and drop the WS mode enum array to map it, but need a little workaround. We map it to any information model variable, copy the reference and paste it down to the data type. Now the data type is mapped and the type conflict is solved. After we finish the mapping process for all variables, we need to export the mapped node set as XML file. To add the mapped node set to a PLC, we need to navigate to the controller. The selected PLC obviously needs to be capable of OPC UA server and preferable OPC UA client functionality. For the tempering machine, we choose to create a new server interface within the OPC UA communication folder. By clicking on the Import Companion Specification button on the top right-hand corner, we can browse to the created XML file. By expanding the tree, we can see the previous mapping between the OPC UA and the PLC variables. Depending on the software you're using, it might be important to activate and configure the OPC UA server before loading the project to your device. In the TIA portal, you need to go to OPC UA server and tick the Activate OPC UA server checkbox. You also need to select the correct runtime license for the server underneath the Runtime License tab. By loading the project into your device, or as in our case, into a soft PLC, we have created the configured OPC UA server. Since OPC UA is device and platform independent, we can use any OPC UA client to browse onto the created OPC UA server. In our case, we are using the UA Expert. After the connection is established, we can supervise any changes on the selected variables. If I force a PLC internal value change, we can see it in the UA Expert. We can also set writable OPC UA variables with the UA Expert. This principle is used by the machine-to-machine communication of the ChoConnect demonstrator. Since you normally wouldn't manually read and change values in the OPC UA server, you can configure a different PLC, let's say the tempering machine, to connect as OPC UA client to the molding plant server. Once again, we browse to the OPC UA communication folder, but instead of a server interface, we create a client interface. By changing the source to online, we can connect to the OPC UA server on the soft PLC. Now the server interface is shown on the right hand side, and we can select variables to drag and drop into the read or respectively write list. By using OPC UA library blocks from Siemens, we can configure the OPC UA client to start up the connection and read or write variables. As you can see, if I change the next article ID of the molding plant, then the tempering machine PLC detects the change via OPC UA.
Thanks Thaddäus for this clear explanation. 3 machine suppliers set up the line for the ChoConnect Showcase. It is now their turn to talk about the history, the possibilities and the future chances of this project. The beginning will be done by Knut Martin from Sollich, followed by Bernd Plies from WDS. He is also the initiator of the ChoConnect project. At the end, Dr. Egbert Röhm from Theegarten PACTEC will give you an outlook into the future.
Hello, my name is Knut Martin. I work for the Sollich KG and I'm responsible for the electrical design department. Under the motto, "What has happened so far?" I would like to briefly introduce you to what has taken place in the run-up to the current event. At the Interpack 2017, the 4 machine manufacturers Lösch Verpackungstechnik, Sollich, Theegarten PACTEC and WDS, together with the automation supplier Bosch Rexroth, showed the practical application of the Open Industry 4.0 standard OPC UA. Connected to virtual production line for chocolate products, 4 locally distributed trade show machines exchanged information with each other, without the integration of an MIS system based on the Weihenstephan standard. The status of the line and all individual machines could be experienced live by the visitors to the Interpack, both at the stands of the 4 participating machine manufacturers as well as the stands of Bosch Rexroth and the VDMA. With ChoConnect, the project partners wanted to demonstrate to the industry how modern communication mechanism from the Industry 4.0 environment can be used to obtain sufficient information to react faster to malfunctions, make production processes more flexible, and increase the overall plant effectiveness in an efficient way. The basis for this was the consistent transparency of machine statuses within the value stream from temperature control and casting equipment to primary and secondary packaging. In contrast to this genuine M2M communication, the previous networking practice provided only rudimentary information such as input and output signals. With ChoConnect, the project partners wanted to give the starting signal for the long-term development of an official standard for confectionery production and explicitly invited all industry participants to participate. I have now finished my part of the presentation and I would like to pass it on to Mr. Plies from WDS.
From my side, also a warm welcome to the presentation. Let me introduce myself at first. My name is Bernd Plies and I am head of the Electrical and Electronic Engineering at WDS. I want to show you some ideas and suggestions how functions and added values could be realized by using a standardized machine-to-machine communication like Weihenstephan standards in the context of ChoConnect. However, first take a look back to the basics and motives for this project from our view as machine supplier. Traditional, the single machines are placed side by side, building a complete line, but nearly no contact to each other and only little communication. In most cases, communication only via the famous potential-free contacts is realized. Vertical data interfaces are still rare and if present, they are individual built and configured. What if the communication can simply be expanded so that we have talking machines and the other machines understand what they are speaking? That means if the line partners could easily communicate in the same language. If we would have a talking tempering machine, for example, which is informing the molding line that mass is available shortly. The molding line can prepare itself, like heating, cooling, start dry run, select and activate the correct recipe. Because the packaging line is well prepared and ready and talking, the molding line can be turned to maximum nominal output and speed for the selected product type. Or, on the other hand, the molding line may talk to the packaging machines that product arrives at the demolding shortly, though all necessary preparations for the packaging of the specified product may be done in the meantime. For example, making ready the necessary packaging material or switching the product flow to the select machines. Even these small examples quickly show what potential lies behind the consistent machine-to-machine communication, especially if it can be implemented quickly and in a uniform way without great effort. Part of the first and early ideas of ChoConnect, there was a vision of a self-controlling and coordinating line. But in the meantime, we are sure that leading systems like MES or ERP will be more and more used in our branch as well. and they are able to coordinate orders, different line partners, and production flow. For this reason, we decide to realize all machine near functions inside the control system of the single machine in the line, to react directly to an event of a line partner. Coordination of the whole line should be done by a leading system like MES. So the higher level system provides all necessary order data for the intended next production sequence via the standardized vertical integration by Weihenstephan standards. This order data, together with the product type behind, then automatically determines via interface the required recipes and parameters of the machines involved in the product manufacturing. Every single machine can activate the right recipe at the right time via the mechanism of the sliding or floating order change. Machine status, fault messages and warnings are communicated in the other direction from the line partners to the control level system in the same way for visualization and evaluation. Thus, the line status and the current line performance are centrally available. The same applies to parameters and all provided process values such as speed, fill levels, temperatures, humidities, values, weights, energy values, and so on. In the horizontal level, all machine-related functions and reactions to the line partners are realized, such as mass preparation and supply can be adapted independently to the fill level of the molding line's funnel, depending on the type and characteristics of the timber and the mass supply. The switching valves or the speed of the supplying pump may be controlled, for example. In the demonstration model, the valves are switched on and off depending on the filling level from the WDS hopper. In a similar way, a function has been integrated so that the WDS molding line adapts to the filling level of the packaging line's buffer store. That means the line speed is regulated automatically in the predetermined limits of WDS. Looking ahead into the packaging, as far as possible, we should be able to reduce major fluctuations or even downtimes significantly. That should already contribute to an increased output with lower losses. The packaging itself uses the same mechanism between the buffer storage and the single packaging machines. Another function could be to react specifically to the process parameters of the neighboring machine or other peripherals in order to avoid faulty production. For example, thanks to the tempering index provided, it would be even possible to interrupt depositing if certain limits are violated. Or you assign the tempering index to the current production of the purpose of traceability. A high level of transparency could be created via shift register systems or mold RFID. The regulations are certainly very specific functions that make sense in every system. However, one can still think of many applications that allow line partners to be connected to each other via plug and play, increasing efficiency and traceability. Let me summarize the presented use cases. From the MES level view, there are functions like floating orders are very interesting, coordinated by MES or another leading system on top. States of single lines are summarized to complete line status, which is available by one click. All errors and warnings are transferred, shown, achieved, and so available for future analysis. Process data is centralized, available as well. From the Sollich or mass preparation view are some advantages like provision of current production speed in both directions, reaction to system status from the molding line and filling level of the line behind. Tempering index may be merged with production data for future traceability. From the view of the molding line, there are interesting solutions like serving the production speed to all systems and the MES system in the near to prevent frequently stops if a line partner couldn't follow. Tracking of process and product parameters for traceability. Or speed control of the molding plant depending from buffer tank level as shown in the demo model. Enabling automatic floating product change when line characteristics like automatic mold exchanger and easy clean equipment is available. From the Theegarten PACTEC or packaging side are following points interesting. By serving filling level of the buffer storage or intake capacity of packaging, the molding plant can smooth adapt to control product outlet. Transfer of product type from WDS line to control packaging routes and materials. Speed control of the packaging line depending on the fill level of the buffer and the status of other packaging machines. And Theegarten provides a function to display adaptation instructions at their HMI. That only some interesting advantages of using ChoConnect with Weihenstephan standards. Thank you very much for your interest and your attention. Don't hesitate in asking questions for more information later. Now I transfer to Mr. Röhm of Theegarten PACTEC for a view in the near future of digital confectionery production. Thank you and bye-bye.
Data-based machine operation is the vision that drives us. Using the example of a packaging machine, I would like to show how future operating concepts can be developed on the basis of the shown connection of the machines. In principle, such concepts are conceivable for every machine in a process and packaging line. The prerequisite for a modern operating concept is the ability of the machine to recognize and display certain events on its user interface, for example, process faults or critical states. Today, a machine requires an operator with as much experience as possible. The task of the machine is to display certain states, to which the operator then reacts with all his experience. In some projects involving universities and machine builders, work is being done to combine the display of states on a user interface with experience in such a way that the operator is better guided in his actions to correct faults and errors. The connection of the machines presented in the ChoConnect project can also be used in the future to transfer and evaluate information about the states of the machines. However, standardized interfaces for communication and data transfer are necessary to make this sufficient. Aspects of a modern UI concept: statistics. Statistical functions are already implemented in the user interface of our machines. All events and states recognized by the machine can be statistically recorded. Especially the observation and evaluation of the temporal frequency of certain states is of interest. For this purpose, it is helpful to scale the time axis of the acquisition as required. An internal logbook stores all data defined as relevant and keeps them ready for a possible data transfer. The compression of this data on the time axis can be scaled individually. Finally, the stored data can be processed into key figures and presented graphically. The user interface offers visualization tools for this purpose. It is also possible to transfer aggregated data to an MES system via the integrated OPC UA interface. Aspects of a modern UI concept: shift protocols. An example of the statistics functions implemented in the user interface is the shift log. Here, different events and disturbances can be recorded in their frequency. Furthermore, this function also offers the possibility to record events. This makes it possible, for example, to record changes of machine parameters and to assign these changes to specific operators. In practice, it can often be observed that the efficiency of process lines fluctuates when the operating personnel changes. In this respect, it can be of interest to evaluate and compare the behavior of operators of different shifts. The shift-related evaluation of the data now makes it possible to visualize the connection between the change of machine parameters, occurring machine malfunctions, and acting operators. Aspects of a modern UI concept: error statistics. Another example of a statistics function is the error statistics. It prepares the error data and displays them graphically in different ways. Thereby, the focus is on repeatedly occurring process disturbances. This function is freely configurable. Thus, it is possible to individually display correlations between events. The different views, the shift-related evaluation, or the display of the most frequent types of errors allow the identification of deficits in operation. From this, potential for action can then be derived to optimize the machines or to train the operators. Aspects of a modern UI concept: vision of process visualization. From the data obtained, it is sometimes possible to identify correlations between machine-related events and machine states. In this case, it can be interesting to make these states visible by combining data and events. The user interface offers extensive possibilities for this. Process values and their changes can be shown on the time axis. Machine parameters or system messages can be displayed as required and depending on the relationships detected. In this way, relationships between these variables can be displayed graphically. Based on experience, areas can be clearly shown where critical machine states can occur. This is the introduction to condition monitoring. From the development of the data and their combination, possible future states can be recognized and displayed. Predictive operation, which recognizes the occurrence of error conditions at an early stage and takes preventive action to avoid these conditions, contributes significantly to increasing the efficiency of the machine and thus of an entire process line. Data-based event display is the vision of ChoConnect. In summary, the building blocks required for a modern operating concept become clear. First, the visualization of machine states supports intuitive operation. A modern user interface is indispensable for this. Second, if it is possible to document the knowledge of experienced operators and integrate it into the user interface, errors can be quickly and purposefully eliminated or even avoided. Third, the collection and forwarding of machine-related data via an IoT platform, such as the one provided by Siemens in the ChoConnect project, allows this data to be evaluated at any point. However, this also requires a standardized language, such as the Weihenstephan standard. And fourth, These prerequisites are necessary in order to integrate technologies such as big data and artificial intelligence into the operating concepts of the future.
Many thanks to all of you for this interesting aspect from the machine supplier point of view. Probably you will be now interested in the functions that will be supported by the WS OPC UA standard interface on the MES, on the manufacturing execution level. This will be shown to you by Dr. Holger Czonka and Niklas Gernbeck from Siemens.
Hello, my name is Holger Czonka and I'm with Siemens Digital Industries in Germany. I'm heading the business development group for machinery manufacturers in the packaging industry as well as in the food and beverage segment. My team and I focus on bringing innovations to our customers, for example, for improving efficiency, streamlining service operations, or enhancing product quality. The previous speakers have already presented many ideas how to increase productivity in the smart confectionery plant by putting more connectivity and digitalization on the shop floor. We will shortly see a live demonstration how such a smart chocolate factory can look like. But let me first summarize the benefits of a uniform data interface and digitalization for both machine builders and chocolate manufacturers. The efficiency boost is based on 3 pillars. First, the standardized data interface that simplifies the line integration. Second, a line management solution that helps you getting a continuous high yield out of your production line. And third, a digital twin of the production line that enables you to do flexible and effective planning of your line layout. Let's see what benefits bring the standardized data interface to the table. On the left side, you see the situation without a uniform data interface that you still find in a lot of factories today. Missing communication standards and interfaces make the line integration of machines difficult and costly. By using a standardized interface, as you can see on the right side of the slide, machine interconnection becomes fast and easy. OPC UA as a vendor-independent communication standard is the way to go here. The Weihenstephan companion specification for chocolate enhances the standard with an information model that is well suited for applications in the confectionery industry. All Siemens SIMATIC controllers support the OPC UA server as well as the client functionality. In addition, the Siemens OPC UA modeling editor simplifies the application development even further. We strongly believe that with Weihenstephan and ChoConnect we can reach the same level of integration efficiency as we have today in other segments, for example in the beverage industry. Whoever delivers the inspection, filling or labeling machine, the data interface is well defined and does not need to be discussed any further. This makes the life of many breweries and soft drink manufacturers easier. Managing the production line in an automated and digital way is another great way to improve the productivity. Without line management, you have to do a lot of manual work that can be avoided. You have to put in more effort for effective job planning and change over at the shop floor. Gather all the information on how the line is performing currently, and if the line is running not so well at one day, you see tally sheets all over the line manager's office in order to find out about the issue and bring the performance back to normal. With our line management solution, you see here on the right side, you have a much smarter approach of tackling your production challenges. You now have an easy way to do the job planning directly at the line. And you always have an overview of your job pipeline. You get the key performance indicators such as availability, productivity, or quality at your fingertips. And if your line has an issue, it's easy for you to find out the cause, and you are soon able to bring it back on track. This is the way continuous improvement is done in the digital age. Siemens' new visualization system, WinCC Unified, is the basis for this line management solution. WinCC Unified uses web technologies for best usability and a pleasant user experience. It's a highly scalable solution from compact machines with small operator screens up to large SCADA applications. The plant intelligence options provide IT functionality on the automation level, such as a shift calendar, KPI dashboards, and other MES-light functions. Another great benefit of digitalization is using simulation for line planning purposes. On the left side, you see the traditional paper-based planning process. The key ingredients for the planner are usually 2D representations of the equipment footprint and the planner's own experience of the equipment behavior. The more complex the plan configuration gets, the higher is the risk of not getting the desired throughput of the line. It becomes difficult to evaluate different line alternatives, and it is hard to estimate the right coverage of operator personnel. Potential bottlenecks might not be obvious and visible. Material flow simulation, on the other hand, makes the whole planning process more reliable and gives you a high confidence in the planning results. What-if analysis for different plant configurations are available at your fingertips. You can be sure to get the optimal operator coverage and avoid costly bottlenecks. In other words, the days and nights of the project lead are much more comfortable. Technomatic's plant simulation is a very powerful tool to fulfill these simulation tasks. This software is widely used in different industries, from automotive up to food and beverage, for simulating event-driven material flow processes, from inbound logistics over discrete and continuous manufacturing steps up to the outbound warehouse. We also use it here in our live demonstration to reproduce the real production process in a simulation environment. My colleague Niklas Gerenbeck will now guide you through the virtual chocolate production. Thank you.
So now we are live in plant simulation. This is our simulation tool for material flow based processes. And this is our digital twin of the ChoConnect production line. Here you can see the temper, the molding plant, and a gondola storage, and two packers which work in parallel. So yeah, so don't be surprised if you see the products are running backwards. This is due to the frame count and the fact that we are simulating in 20 times real time. So I could change to simple real time, and then when I zoom in, you will see every product is running forward. So yeah, we use this simulation to get realistic data from this production line, and yeah, we achieve this. Let me switch to a single machine. We achieve this by simulating the material flow of the machines. So in the bottom you can see the functional description of the material flow of a single machine. At first here you have the inlet where the products arrive. Then there is a state machine where we simulate Weihenstephan compliant states. Next one is product ejection. So regarding to a specific factor, we can eject some products to gain something like equality. And at the end, there is the outlet, and in a whole line, there will start the next inlet of the next machine. In addition, we simulate stochastical fault behaviors. So from time to time, some machines will generate an error state, and these different states we can monitor with our MES system later on. Next one is here we have PLC Sim Advanced. We simulate our PLCs, so we have 5 virtual PLCs which are connected to plant simulation, and in each PLC there is a OPC UA server and a OPC UA client, and the OPC UA server will obtain the data from the simulation, and the server has the OPC UA companion specification interface designed after the Weihenstephan standard. And each machine can communicate to their neighbors, and so the data for the order will be reached through the line from machine to machine. And in addition, it is possible that maybe if one of the packers has a standstill, the second one will detect it and could raise up his production speed to avoid a tailback in the whole production line. Now this is a line visualization of ChoConnect, and we realized it with the new HMI platform WinCC Unified. On the left hand side you got a short overview over all machines which are in the line, and you can track their state or their production speed, and so you get a fast overview. For example, here you can see now molding plant is on changeover. So in the middle there's a Gantt chart. This Gantt chart tracks every state of every machine in the production line, and you can see for every point of time which machine had which state. For example, over here there's a molding plant, and you can see here to this time there was an equipment failure, and it lasts 1 minute and 26 hours. So you can do this for every machine and for every state, and the period is tracked of the whole state, and the appearance frequency is also tracked here. In addition to that, you can track micro stops. So same as before, every micro stop is tracked by the Gantt chart, and you can see the amount of micro stop for each machine and for each different state. On the right hand side there are the actual KPIs, and this is the performance and the availability of the whole line. Right now, the availability is a bit less because there's a changeover in the whole line. So there will be a change from product A to product B. Yeah. Then every machine has its own dashboard where you can see the mode, the program, and the state according to Weihenstephan standard of every machine, and there are some specific measurement values, for example the current production speed or the chocolate temperature, or for the temper there are some more temperature measurements. So there are different dashboards for different machine types. Here you can see there's an order change. At the output there's order 35, and at the input there's already order 36. According to the different orders, we have an order overview. It's kind of waiting queue. Here you see the actual processed orders and the orders who will be next. Also, you can create a new order by typing the order ID, the quantity you want to produce, and the specific article. When an order is completed, the whole KPIs will track according to this order, and you can check this afterwards in this overview. So you can compare the KPIs of different orders, and you can see here the performance, the quality, and the availability of the line for this specific order. And also, if you multiply these three factors, you get the overall equipment efficiency for this specific order in the production line. There are some more measurements for some single machines. You can see here molding plant Packer 1 and Packer 2, and for this you can compare, for example, two machines. You can check why Packer 1 has a much more higher availability than Packer 2, or why does orders where you produce the same article have different qualities. So with this information you can check back your production line, and you can improve the whole efficiency of your production line. Last but not least, there are some alarms. You can see here alarms we simulate in plant simulation, like I said before, and you can filter different alarms, and you can see these are historical alarms which occur in the past, and maybe we can filter for molding plant, and now you see every alarm for molding plant. You can see here was an alarm, and it was incoming to this time, and it was outgoing to this time. So you can additional for to the KPIs, you can check why there was maybe a standstill or something like that.
Thank you, Holger and Niklas, for this nice presentation about the exemplary MES solution. Finally, I'd like to thank all of the speakers and all of the partners at this webcast and the partners that worked together to set up the ChoConnect Showcase. These are the machine suppliers Sollich, Theegarten PACTEC and WDS. The company Siemens as an IT system provider. Many thanks also to the VDMA, Food and Packaging Machinery. The VDMA, the German Machinery Association, sponsored and financed the development of the WS OPC UA companion specification. At the end of this webcast, I like to invite you to join us and to work together for the digitalization of chocolate production. If you are a chocolate manufacturer, then request the preparation of your new machines or systems in the future, the preparation with OPC UA client and server according to the WS OPC UA companion specification. And please help us to develop, especially for your branch, the new library WS ChoC. We will need some funding to do this work, of course, but also we need your expertise, because you are the chocolate manufacturers and you are necessary to develop a future standard for your needs. The basis is there, the WS OPC UA companion specification, but we would like to specialize this basis for your branch. If you are a machine supplier, all the mentioned machine suppliers that work together in the ChoConnect project so far are open to work together with other machine suppliers, so join our group and offer your machines with added value through an OPC UA client and server according to the WS OPC UA companion specification. And if you are an IT system provider, you've seen Siemens here as an example, but others also are invited to join us to implement OPC UA clients, because this will allow a fast and efficient and cheap installation of IT solutions according to a plug-and-play concept. Also, you as IT system providers are invited to join us to develop WS ChoC. So finally, I want to thank you. Contact us if you are interested in working with us together, but with WS ChoC. And many thanks for listening to this webcast.